So, welcome to the fourth lecture involving Gibbs free energy and entropy. So far we've used the Gibbs free energy as a way of calculating whether a reaction will take place or not, and if it takes place, whether you get to an equilibrium and what the equilibrium constants are for the reactions that work under those conditions. What else do we have to consider? Well, there are several other things that we need to clear up before we finish our discussion of Gibbs free energy. So let's look at a simple, straightforward reaction. Liquid water plus ammonia dissolved in solution goes to form ammonium cations and hydroxides. We of course know this is what happens because we've done this equilibrium several times for Arrhenius acid-base reactions. Take a minute, look up the delta H's and the delta S for these compounds, and figure out the delta G0 before we go on. Not surprisingly, the delta H of this reaction is close to 0. After all, to create this reaction, we're going to have to break one bond, and we're going to create one bond in return. And so that's going to eventually come out to 0. And so part of the major part of the driving force in this reaction, of course, is the entropy change. And that's interesting, because you'll notice that the delta S0 for the hydroxide is in fact negative 11. How can you have a negative amount of entropy? A perfect crystal at 0 degrees Kelvin would have 0. How can the hydroxide have a negative entropy? Well, you have to keep in mind, the hydroxide is in solution. For a pure compound, then yes, the S0 is an absolute value. But in solution, we've had to rebalance the scale because many things have an interaction with water when they dissolve. And so that's a delta S for the hydroxide rather than simply an S0. Still, how do you get a negative entropy change? Well, we said the whole reason that ions dissolve in solution is because they surround themselves with water molecules. Well, what that means, of course, is they in fact some ions will in fact force the water into being more organized than the water would be all by itself. So actually having those ions, like calcium ions or silver ions in solution, actually causes the process to have a negative entropy change because they force the water into more organization than the water would have without the ions present. So we can figure out the delta G0 plus 27.5 kilojoules. That means it's unfavorable. Well, it's unfavorable for 1 mole of ammonia and 1 mole of water to form 1 mole of ammonium ions and 1 mole of hydroxide ions. But of course, that doesn't mean it doesn't happen at all. It actually does happen. Ammonia qualifies as a base. And therefore, what we have here is, surprise, surprise, an equilibrium. So, RT log K equals delta G0. So the log K equals delta G0 divided by RT, and so minus 27,500 joules divided by 8.314 joules per Kelvin divided by 298 Kelvin gives us minus 11.1. So the equilibrium constant for this reaction is 1.5 times 10 to the minus fifth. So at equilibrium, delta G0 equals RT log K. Well, delta G0, of course, is also equal to delta H0 minus T delta S0. And so since they are both equal to delta G0, they must be equal to each other. And so we have RT log K equals delta H minus T delta S. We can divide both sides by the RT. And we get delta H0 divided by R times 1 over T minus delta S0 over R. What that means is if you plot the log of the equilibrium constant versus 1 over t for a reaction, the slope of the line will be delta H divided by R, and the y-intercept will be minus delta S0 over R. So this is another way we have of getting values for delta H and delta S. We can simply measure the equilibrium at several temperatures. One of the equilibriums we know real well is Kw, auto-ionization constant for water. At room temperature, that is 25 degrees, 1.0 times 10 to the minus 14th. If you cool it off, it becomes 1.14 times 10 to the minus 15th at 0, and 5.47 times 10 to the minus 14th at 50 degrees. So using this information, calculate delta H and delta S for the reaction for the auto-ionization of water. So the log of the equilibrium constant at 273, 298, and 323 Kelvin respectively, 34.41, 32.24, 30.54. Take the reciprocal of the temperatures and our plot, and we see from this equation that the slope of the line is 6832.7 times 8.314 joules per Kelvin per mole, and we get that the heat of formation for that reaction should be plus 5,608 kilojoules, which is about the accepted value for the reaction of protons and hydroxides to form water molecules, the reverse reaction. As for the delta S, minus 9.3592 times 8.314 is minus 78.8 joules per Kelvin. And from the calculation we just did above, with the hydroxides and water molecules, we get a value of minus 81. So again, we're getting a good general area number for the delta S as well. And so we have another way of getting delta S's and delta H's. Instead of a reaction, let's consider a simple process. We have gas and a piston, and it's at 2 atmospheres pressure. The outside pressure is less than 2 atmospheres. What's going to happen? What's obviously going to happen is the gas will push the piston back. It will do work. It'll apply force and change the volume. It'll move the piston. So work is being done. But there's no reaction. There's no delta H. So what's the driving force of this reaction, this process? And of course, it's the entropy term. As the piston moves, the gas has more volume, so its entropy is going up. And it'll keep going up until when? It'll keep going up, the piston will keep moving until the pressure inside is equal to the pressure outside. And then it'll come to a stop. The change in entropy term will have come to 0, which means the delta G will be 0. The process will have stopped by itself. So how much work was done? Well, that becomes simply the straightforwardly, what was delta G to begin with? And that's what delta G is. It represents the greatest amount of work that can be done by the system before it either runs out of incentive or reaches equilibrium. In this case, it's reaching equilibrium, the pressure inside and the pressure outside being the same. And so that's what delta G represents, the maximum amount of work that can be gotten out of the system. Which brings us finally to a nice straightforward reaction. Hydrogen gas and fluorine gas form hydrogen fluoride. The fluorine obviously wants to react with anything since it doesn't like being bonded to itself, and so this reaction is very favorable. In the first place, it is conspicuously exothermic, and the fact is, it actually includes a raise in entropy. If you consider a molecule of hydrogen, 2 hydrogen atoms side by side, and you turn it around, it looks the same. The same thing for the fluorine. But if you take the HF and turn it around, it looks different. One has the hydrogen on the left and the fluorine on the right, and the other one has the fluorine on the left and the hydrogen on the right. What sort of indicates that HF has more choices than either the hydrogen or the fluorine molecules do by themselves. So not surprisingly, this includes a small rise in entropy as well. So, negative delta H, positive entropy change, this reaction should always run really well. So does it run 100%? Does the reaction run totally? Well, no. And why not? Well, consider, if we have 100 molecules of hydrogen and 100 molecules of fluorine, and they all react, we'll get 200 molecules of HF. And we'll get the maximum amount of energy out for the reaction. And the entropy will maximize. Well, no, actually it won't. Consider, suppose one of the molecules of hydrogen and one of the molecules of fluorine does not react. We end up with 198 HFs and one hydrogen and one fluorine molecule. And the point is, which one of the 100 hydrogens didn't react? Which one of the 100 fluorines was the one that didn't react? Is this giving us choices? Yes, it is. And the point is, reacting that last hydrogen and that last fluorine together is therefore going to significantly reduce the number of choices we had before. And so it in fact would include a distinct drop in the entropy. And so what we see is the reaction does not go 100%. Instead we get, surprise, surprise, equilibria. It is never favorable for the entropy for the reaction to run 100%. That always ends up reducing somewhat, somewhere, the choices the system has. That is the amount of entropy. And so while reactions will be extremely favorable and might run to an undetectably small extent, nonetheless, you never get 100% reaction. And that brings us to the end of Chapter 17, dealing with thermodynamics and entropy. The next chapter is Chapter 18, dealing with galvanic cells. The homework's due on Wednesday for Chapter 17, and I'll see you then.